In this module, we'll extend the two independent samples comparison to more than two population or process means. We'll develop an overall hypothesis test using a one-way analysis of variance. We'll also talk about multi-comparison tests among the means when the ANOVA is significant, and Tukey's method of controlling type 1 error rate when conducting multiple comparisons. Some examples of when one-way analysis of variance can be applied are comparing the effect of 5 different brands of 89-octane gas to see which give the best miles per gallon, comparing the effect of 4 different additives effect on the gloss of a paper, comparing the effect of year of undergraduate student on the grades of the students in basic statistics class, and comparing the effect of 6 different cell configurations on the rates of parts produced per hour. Let's consider the compression strength of 4 different types of corrugated boxes. Assume that we have a machine available for testing. How would you design the experiment? For instance, how would you select the boxes to be tested? How many boxes of each type would you test? Does the order in which you test the boxes make any difference? These are some of the things you have to think about when designing an experiment. Let's assume that the boxes were reasonably sampled from the process and that the testing order was random. Here's the data from testing the compression strength of 6 boxes of each of the 4 different types of boxes. In this case, the same number of each type is tested, although this is not technically necessary. It keeps the explanation and ideas simpler for now. You'll notice also that we have calculated the sample mean and sample standard deviation for each type of box. We are interested in whether the underlying population means are different. In other words, whether some types of boxes have an inherently higher compression strength. It's always a good idea to plot the data. Here we see a grouped dot plot that shows the 6 individual observations for each group all in one display. It appears from inspection of the graph that box type 4 has a lower compression strength than the other 3 types. We may not need to do a formal analysis in this case, but let's follow through the example to see how it would work. As we said on the last slide, it's pretty clear that box type 4 has a lower mean than the other 3 types. More generally, how would we go about doing a formal test for differences among means? Well, we know how to test whether 2 means are different from one another, t-tests. We could just do a bunch of those, right? How many are there? If we conduct all possible 2-sample t-tests, and there are 4 groups to start, then there are 4 choose 2 different two-way tests, or in this case, 6 different 2-sample t-tests. That's a lot of tests. We'll come back to that later. For now, let's try to develop a single test to see if there's anything going on with 4 means. We'll start with some assumptions. Each sample comes from a population, potentially with its own mean, but with a common variance. Furthermore, the observations are all sampled independently of one another. The null hypothesis is that all the population means are equal. The alternative is that they're not all equal. The fancier way of saying this is mu sub I is not equal to mu sub j for some I not equal to j. This slide illustrates 2 types of variability in our data. First, we have the red circles, which illustrates the variance within each group. Secondly, the green circle, which represents the variability across the groups. But if the null hypothesis is true, then these 2 variances are related to one another. The variance within each group is an estimate of the sigma squared, while the variance across the group is the sigma squared divided by j, the number of groups. If we pool the variance within the groups, we get an estimate of the mean square error. If we take j times the variance across the groups, we get an estimate of the mean square treatment. But if HO is really true, then both these quantities estimate the population sigma squared. If these 2 quantities, mean square error and mean square treatment, are 2 estimates of variances, then what test have we used in the past to see whether 2 variances are equal? The F-test. The F-test will have I minus 1 numerator degrees of freedom and I times j minus 1 denominator degrees of freedom, where I is the number of groups and j is the number of observations per group. If the ratio of the two mean squares is sufficiently large, then we'll reject the null hypothesis and favor the alternative. The mean square treatment will always be equal to or larger than the mean square error, so the F statistic will always be greater than 1.0. This allows us to treat this as a one-sided test, so we look up the critical cutoff value without needing to split the alpha between two rejection regions. You can verify for yourself in the F table in the back of the book that with 4 groups and 6 observations per group, that we get 4 minus 1 equals 3 numerator degrees of freedom, and 4 times 6 minus 1 equals 20 denominator degrees of freedom, and with an alpha equals 0.05, we get a cutoff value of F of 3.10. We'll reject the null hypothesis if all the means are equal, if our calculated F statistic is greater than 3.10. Our F statistic is 42,450 divided by 1,691.5, which equals 25.10, which is certainly greater than 3.10. Therefore, we reject the null hypothesis. So where does ANOVA, or analysis of variance, come from? The idea of analysis of variance is to have a structured way to decompose the total variability into its individual components. Here we are separating the within group or error portion of the variance and the cross group or treatment portion of the variance. This can be done using the sums of squares. But what are sums of squares? Here we see the formulas for the calculation of the sums of squares total, sums of squares treatment, and sums of squares error. Take a minute and try to figure out how these formulas work. You'll notice that the sums of squares total is the sum of squares treatment plus the sums of squares error. This will always be the case in the one-way ANOVA. Knowing this also gives us a way to check our calculations. This table is commonly referred to as the ANOVA Table. Here we can see that the mean square for treatment is just the sums of squares of treatment divided by the degrees of freedom for treatment. Similarly, the mean square for error is just the sums of squares error divided by the degrees of freedom for error. But those are the same mean squares we saw before. The mean square for treatment is just j times the sample variance of the means, and the mean square for error is just the pooled sample variance. As before, the F statistic is formed by dividing the two mean squares. The p-value in the table confirms that the F statistic would be rejected at our alpha equals 0.05 level. It's easy to imagine questions that present parts of this table and ask you to fill in the blanks based on these known relationships among the quantities. This F test gives us an overall test of statistical significance which, if rejected, leaves us still with a lingering question. If we know they are not all equal, how do we know which ones are different from one another? When the null hypothesis is not rejected, the analysis is terminated because no differences among the means have been shown to exist. But if the null hypothesis is rejected, the experimenter will usually want to know which of the means are different from one another. This further analysis is called multiple comparisons. We could calculate a confidence interval for each of the k times k minus 1 divided by 2 pairwise differences. Then if the resulting intervals do not include 0, then those means are significantly different from one another. But if we conduct all those tests, each at its own error rate, then the chance that we make at least one mistake is compounded. So we need to come up with a way to control the error rate of all the tests together. Consider a situation where we calculate a 95% confidence interval for the difference between treatment 1 and treatment 2. Suppose we calculate a second 95% confidence interval for the difference between treatment 1 and treatment 3. Since the confidence intervals are independent of one another, the joint confidence level is 0.95 times 0.95, which is 0.90. If the joint confidence level is 90%, then the simultaneous type 1 error rate is 10%, twice what it was for each individual test. So if we need to maintain the simultaneous level at 95% for two intervals, we would need to do the individual confidence level for each interval to be 0.975, which corresponds to alpha of 0.025 rather than 0.05. The larger the number of intervals, the lower the alpha levels for each interval must be in order to maintain the 95% confidence level. This is one way of controlling the family-wise error rate. So one way to control the family error rate is to lower the error rate on each of the individual intervals or hypothesis tests. Start by taking the desired family error rate and divide by the number of intervals to be created. Suppose we want to control the family error rate at 5% for 5 tests. Let's try conducting the test at 5% divided by 5, or 1%. We can see from the formula that the overall family rate is 0.049. Very close to our target of 5%. There are 4 means, so there are 4 choose 2 pairwise comparisons to make. That's 6 possible pairs. So we could conduct each test at a p-value of 5% divided by 6, or 0.83%. But that would be a very conservative approach. Tukey's procedure for creating simultaneous confidence intervals for all pairwise differences make use of a probability distribution called the studentized range distribution. The distribution depends on 2 parameters, numerator degrees of freedom m and denominator degrees of freedom n. Let q of alpha at m and n be an upper-tailed critical point of the studentized range distribution with m and n degrees of freedom. These values can be found in tables in the back of the book. A simultaneous confidence interval for all pairwise differences based on Tukey's method is shown here. We'll be interested in whether the confidence intervals contain 0 for each pair. Here's the ANOVA table and the sample means for our earlier example. If we start with an alpha equals 0.05, k equals 4 groups, with n equals 6 observations per group, we can develop a confidence interval for the difference between group 2 and group 1 as shown here. Since the interval contains 0, we would conclude that type 1 is not statistically different from type 2. Since we are only interested in whether or not 0 is in each interval, there's an easier way to identify significant mean pairs. First, we calculate double, a width required for significance. Then we list the sample means in increasing order and underline the pairs that differ by less than W. Any pair of sample means not underscored by the same line corresponds to a pair of population means that are statistically different. Here's the method applied to our example. The W is calculated to be 66.5, and the only mean that is statistically different is box type 4, which is consistent with what we saw in the dot plots. Here are some of the things you should be able to do with regard to analysis variance as a result of viewing this module and doing the associated assignments. Here are some of the things you should be able to do with regard to multiple comparisons as a result of viewing this module and doing the associated assignments.